Hello and welcome to another presentation on graphs and gradients. Here we're going to be looking at the standard graphs which students need to learn for GCSE, how they can tackle graph related questions, and then we're going to be looking very briefly at the topic of gradients, which will be covered in more detail in Algebra 3. But as I've mentioned already, I think in Algebra 1 gradients is a crucial idea, and yes, it needs to be emphasised to students, particularly those going on to study A-level. Okay, here you're presented with a heart-shaped curve. Now there's, I like to show this to my students sometimes, just to try and get them interested and engaged in graphs and how we can model most shapes graphically now, really. Just take video games for an example, all of that is really just, well, I think it's done with matrices actually, but it's certainly done with mathematics, that's for sure. So we can certainly come up with any patterns we like using maths, using the appropriate mathematical equation. The equation I've used here for this one just involves cube roots and square roots and some x squareds, and that's it. If you use GeoGebra as I've instructed you to download, you can certainly have a go at graphing that and seeing what it looks like. Okay, let's have a look at some of the standard graphs that students need to learn for GCSE then. Okay, we've got straight lines, quadratic graphs, cubic graphs. That is a new entry actually in the new syllabus, but they've mentioned cubic graphs. I'm sure you picked that up on the specification. Exponential graphs, reciprocal graphs, equations of circles, and finally trigonometric graphs. Now, I'm going to look at all of these today except the last one, which will be covered in Algebra 3, mainly because trigonometric graphs are worth spending some time on in the way they transform, and they tie in quite nicely into function transformations, which is another idea we're going to be looking at in Algebra 3. So, yeah, these are the graphs, the standard graphs, if you like, that students are expected to learn for GCSE. Now, I'm certain you'll be familiar with y equals mx plus c. That is a standard straight line equation, and naturally the m stands for the gradient and c stands for the y-intercept. But there's no reason why we've used m and c, no good reason anyway, it's just a convention. And I could have used a and b, and if I had, I think you'd see a lovely little pattern occurring for straight lines, quadratics and cubics, and it would have been nice to retain that pattern really, because those first three graphs are all examples of polynomials. Polynomials are lovely topics of investigation in and of themselves, and you can certainly take it beyond cubics. I always, after mentioning cubics, point out quartics and quintics and what they look like, because it gives students an idea of what this whole family of curves achieves, and certainly it just it seems to add an extra hump each time you go up one on the power on the x, but certainly that's a nice little topic which is worth investigating on its own. Then we have exponential graphs, which are of the form y equals a to the power of x. It's important to note that this time the variable x is the power here, unlike in the polynomial graphs where the variable x was the base, not the power. The power was constant and also a whole number for the polynomial graphs, but for exponential curves the power x is the variable. Okay, then we've got reciprocal graphs, which is anything of the form y equals 1 over x. They often forget what those graphs look like. We're going to have a look at those in a second. And then finally, the last ones we're going to look at today are equations of circles. Now, I believe that some exam boards anyway are thinking about introducing equations of circles which don't necessarily have the centre as the origin. If the centre is the origin, then the equation is simply x squared plus y squared equals r squared. However, if the centre is somewhere else, let's say the coordinate AB, then we get the following equation for a circle. So that general equation of a circle represents a circle radius r, centre AB, and I'm sure some of you will remember that from your A level. Under that I've put down the trigonometric graphs just because they're certainly part of the course, but we won't be looking at them this time. Okay, I'm going to ask you a question here. These are some straight line equations. Let's get you doing something. I hope you can see clearly the numbers on the axis there, because they are going to be vital to finding the equations of those lines. Just pause the video for a moment and try and find the equations for those lines. A was naturally, now I've rearranged A and in many ways it's the most difficult one, but if you've got an answer of y equals minus 4/3 x plus 4, that is correct, yeah? I've simply rearranged it into a much nicer format and a much better way of representing it really. It's nice anyway if we haven't got any fractions in our final equation, and that's why I've rearranged A. The rest of the equations I would suspect you've probably got exactly the same as mine. B was just y equals 2x minus 4, so that is a natural one to put in the form y equals mx plus c. C, you've probably got actually a slightly rearranged version of mine. You've probably got y equals a third x plus 1. That's absolutely fine, but once again I've times it by 3 just to get rid of the fractions at the end. The only reason we do that is because it looks a little bit neater and tidier. And then finally we've got the straight line equations x equals 9 and y equals minus 5. I hope that wasn't too difficult for you. I hope it was just a little bit of fun, keep you thinking. And what I'm always at pains to point out when I'm doing any graphical representation of algebraic equations is that that equation works. What do I mean by works? I mean that pick any point on those lines, plug it into the equation, and it satisfies the equation. If they're ever worried in a graph matching activity about which graph goes with which equation, pick the points, pick the coordinates, and demonstrate to them that it works. Okay, let's have a look at some quadratics. I would like you to try and sketch the following curves because we've already covered this in Algebra 1. So have a little go and see if you can go through the routine. I'm sure you remember the routine. Go through the routine to try and sketch these quadratic curves. I don't want you to draw a little table of values, which is what the students often want to do. I'd like you to do it just as a quick sketch. So all I really want to see are the x-axis intercepts and the y-axis intercepts. Pause the video and off you go. Okay, A, hopefully you can see after you factorise it, because that's always what we should do if we're trying to sketch a quadratic curve or a cubic curve or a quartic, any polynomial curve. Try and factorise it, set it equal to 0, and you'll be able to find the x-axis intercepts. So that first quadratic equation factorises to give y equals x minus 3 times by x plus 1, both of those in brackets. That gives you, of course, a positive 3 and a negative 1 for the roots of the quadratic. We call the x-axis intercepts the roots of the quadratic. That gives us, if you look at it, the quadratic in the middle of the page, which is a smile rather than a frown. Remember, positive x squared always results in a smile. I also know that it goes through minus 3 on the y-axis, because when x is 0, y is minus 3. Likewise for b, you can factorise this doing difference of 2 squares, but that's going to give you 1 plus x, 1 minus x, and because this is a minus x squared, this one's going to be upside down. But sure enough, after you solve 1 plus x, 1 minus x in brackets equals 0, you're going to find that x equals 1 or minus 1. And when x is 0, y is 1 as well. That's how we get that one. Finally, for the last one, y equals x squared minus 5x plus 6. Well, that factorises to brackets x minus 2, close brackets x minus 3 in the next brackets. That gives me intercepts of 2 and 3 on the x-axis, and if x is 0, y equals 6. Okay, let's have a look at some cubic curves. This time I'm showing you the picture of the cubic, and I would like you to try and come up with the original equation. Now just think how quadratics work here. If we've got the factorised form, then we know where the curve is hitting the x-axis. Well, here we know where the curve is hitting the x-axis, so let's try and give the factorised form. Okay, pause it and try and write down the equations of those two cubic curves. Okay, so for the first one, we can see it's hitting at minus 2, 0 and 1. And so we've got y equals x times x plus 2 times x minus 1. Naturally, you can write those down in any order you like. And for the second one, we've got y equals x plus 1, x minus 1, x minus 3. Simple as that. I hope you're enjoying this because we're going to do a few more now. Now, I wonder if you can recognise which of the next following graphs is which. Okay, so we've got exponential and reciprocal curves. So, hopefully you can see on the left, this is a rather typical curve of the form y equals k over x, anything over x. Now, if it went through the point 1, 1, I would assume it was the curve y equals 1 over x, but this one goes through the point 1, 3. Now, if you write down y equals k over x first, and then plug in a point on the curve, you could find the value of k there. That's how I can quickly establish that the one on the left is y equals 3 over x. For the one on the right, I always like to point out the exponential curves. These do come up in some very tricky questions, as we'll see in a couple of slides. But the general shape of them is a curve which is increasing very, very quickly. In fact, that's where we get the word exponential in the English language. If I say something is increasing exponentially, I mean it's growing very, very fast. Well, that's exactly what happens if you sketch the curves y equals 2 to the power of x or y equals 3 to the power of x. Their rate of increase is very, very fast indeed. And in fact, it is proportional to themselves. That's how we get the graph y equals e to the power of x, because it is equal to itself, its gradient, its rate of increase. Finally, we have the circles. I've got 2 circles sketched there for you. Now, the middle circle is just x squared plus y squared equals 9. I know that because it has a centre of 0, 0. But what I believe they're going to start testing you on in GCSE are circles that have a different centre. Well, the bigger circle here has a centre 1, 1. And so we're going to need to do x minus 1 squared plus y minus 1 squared equals the radius squared, and the radius of that large circle is 5, and therefore it equals 25. The circle's width, or circle's radius, sorry, is always squared, and that is what x squared plus y squared is equated to. Right, let's have a look at one of the really nasty questions that you can get in GCSE. This is about as difficult as it gets. Okay, let's say we have a curve of the form y equals ka to the x. And this curve goes through the points given by the coordinates 1, 7 and 3, 175. And we've got to find the values of k and a, given that a is a positive constant. Now, I would like to point out that they have made this even more difficult than this in the past by making the numbers really awkward and putting it on a non-calculator paper. This is actually reasonably friendly with the values. Pause the video by all means if you want to have a go at this first, or wait for the solution to pop up in a second. Okay, so let's substitute the values in. We get 7 equals ka to the power of 1 by plugging in 1, 7, and 175 equals ka cubed by plugging in 3 and 175. Now, students are often perplexed as to how to solve this kind of system of simultaneous equations. I would put it like this: they can use substitution, because you could rewrite equation B as 175 equals ka times a squared, and therefore I could plug in 7 as ka into b. But I don't like to do it like that. I always prefer to divide, because if I've ever got a number to the power of something and I've got to find either the power or the base, if I just divide, we can just use index laws for working out the division. This will get rid of k, because k divided by k is 1. So we have 175 divided by 7 is 25. Ka cubed divided by ka is just a squared. So 25 is a squared, and therefore a is 5. Some of you might think, hang on a second, why can't it be minus 5? Well, it did say that a was a positive constant, so I know a is 5, and therefore k, plug a is 5 back into a probably, that would be the easiest way, and you can see that k is going to be 7/5. Okay, let me just quickly mention what the new syllabus also asks you to do, because this is going to come up in the next little exercise that I set you in this part of the course. Gradients and graphs. Well, if you ever want to know an estimate for a rate of change, or the gradient as it were, remember the gradient and the rate of change, you can use those phrases interchangeably, they mean exactly the same thing. The gradient is the rate of change of y with respect to x. Under the new syllabus, they are asked to find the gradient of a curve, but without using calculus, at least as far as we can tell at the moment. All of the new textbooks which have been written for the new syllabus don't seem to contain any dy by dx from what I can tell. Now don't worry, I will be taking you through some dy by dx as a reminder of how calculus works, but that's going to come up at the end of the course. Initially, at the moment, I just want to show you what is going to be coming into the new GCSE. Now, if you ask to find the gradient of curve without using calculus, you're going to have to use a carefully constructed tangent. That's the only way, really, that you can find a tangent to a curve without using calculus methods. It is the original calculus, if you like, finding the tangent to the curve. And so here's a little picture of that happening. It's with GeoGebra again. GeoGebra is fantastic for representing these kind of things, and before doing an exercise where I get students to construct tangents, using a ruler and a pencil, I would show them on GeoGebra the tangent actually sliding around the curve, so that they can see that there is only one unique tangent at any point to the curve. They kind of sometimes say, well, hang on, can't I move the ruler around a bit? And I always have to point out, yes, but when you move the ruler, you're actually moving the tangent around the curve. So at any particular point on the curve, there is just one tangent. Once you've drawn that tangent, you can naturally draw a little triangle on the straight line, and then conduct the rise over run equation. And that's exactly what GeoGebra has done for us here. It's roughly estimated the gradient as 4 because the rise is 3.99 and the run is 1. 3.99 divided by run, roughly speaking, is 4. And that's really all they're going to be asked to do. That's not too bad, and you'll see a question like that coming up in the next little assignment that I've got for you on it's the document entitled Graph Questions and Graph Answers. But yeah, there's some quite interesting questions in there, including one on the trapezium rule as well, so you can get a good idea of what is coming into the new GCSE. All this stuff incidentally used to be in the GCSE. It's only been out of the GCSE for about 10 or 15 years, but it certainly was in the GCSE when I took it. Okay, right, I hope you enjoyed the presentation. It's just a little reminder. It's certainly, I'm sure, is going to be for many of you just showing you things which I'm sure you need maybe a bit of a refresher course on, but I'm certain you'll remember exactly how to do it. Okay, thank you for listening, and I will be joining you soon in Algebra 3.